All right, so we are going to study about the maximum and minimum values of a multivariable function in this video lesson. And so before we get started, I have to mention the skills that I am specifically focused on in this lesson is going to be the skill that we find maximum and minimum value for a two-variable function. And then in a later lecture, I should be able to deliver a lesson that will introduce a more universal method of how we can find maximum and minimum value problem on a general multivariable function. And so once again, the method we learned here, the method being delivered here, is mostly is limited to function of two variables. All right. So other than that, let's begin. All right. So now, in order to have a successful understanding and in order to have a successful lesson here, I highly recommend that you bring in as much of your understanding about calculus 1, the single variable calculus, into this lesson as possible, especially all of those skills of how you found maximum and minimum value problems in a single variable calculus course. All right, and so that the transition can become a lot easier here. All right, and so now in what I said, that bring in as much understanding of your calculus 1, the single variable calculus, in terms of solving a maximum minimum value problem. What I mean here is as follows. So now when we're working with a one or a single variable function, f of x, then the graph, we have seen that back in our days learning about single variable calculus, then the function has peaks and valleys, right? There are points that it's raising high and peaks out, and then there are points that the function hits low. Like that. So those are highs and lows. Like that. Back in our days, we call that local maximum and local minimum right here. And then those usual understanding that we have seen back then, right? So now when you transform over to a function of two variables, let's say we have a function f of x comma y. And again, as I said earlier before we begin, what the method we're about to learn here is only limited to be able to handle a function of a two variable function. And so I'm trying my best to draw a sketch here, but a function of two variables has a graph being a surface. And so the graph can be like this. It gives me a high peak like a mountain, and then at some point it's gonna give me a low peak. Okay. And so I hope viewers and students viewing this lesson can kind of imagine the mountains and the valley I'm trying to indicate here. And so very similar to that kind of idea we have learned back in one variable function, single variable function. A graph for a one single variable function has peaks and valleys. So just like that, a function of two variable, right, or a two variable function has mountains and valleys, just like that. There's a peak point and there's a valley. There's a hole. Okay, there's a peak point and there's a pit. Okay, and so we're gonna learn that methods to find how high that peak point reaches and where can that peak point be. Okay, and so just like in the day, at least for anyone who study with me, then I tend to explain carefully. Anytime we're looking for maximum or minimum value, there are always the questions about where we reaches the maximum on a function and where we reaches the minimum, and then how high does it reach for the maximum or how low does it reach. So always two questions. And so the same exact understanding when we carry that over to a function of two variable, then we have to first identify where the function reaches a mountain, the peak of a mountain, and where the function reaches to that bottom of a valley right there. So, and then how high would it reach and how low would it reach? Okay, and we're gonna go through all of those. Okay, and so now really let's begin right here. All right, so now to begin with our lesson here, I am going to start out with a function. And so allow me in this lesson here to approach the problem, to approach the lecture completely based on one big problem. We're starting out with a given function, and we're going to go through every step to find all of the maximum and minimum values problem. And then you're going to, along the way, we are going to study how and the technique, how and the method, how we find the maximum minimum value problems. Okay, so now we are starting out with a function given. Let's say I chose a function f of x comma y equals 8x minus 8y over 8x squared plus 8y squared plus 1. So this is the function that we're starting out with. Okay, and we want to find the maximum and the minimum. Okay, the maximum and the minimum. And so now let me quickly swing over to the computer station and show the graph. So of course, it's not easy to make a hand sketch of the graph for this, the surface being the graph for this function. So we're going to need to use a lot of technology. So there will be a lot of instances where I swing back and forth between here and the computer station right there to show the graph of the function on screen. Okay. All right, so now with the blank graphing space right here, this is the graph for our function. 8x minus 8y all over 8x squared plus 8y squared plus 1. And so obviously, just like what I was describing earlier, a surface like this has a mountain and it has a valley. So this mountain right here and this valley right here, think about that similarity have we learned back in the days of that we're studying about calculus 1. Those mountains and those valleys right there, they happen at the critical values and all that. Okay, so we're eventually going to learn through all of those. But now let's have one closer look at the graph right here. You see, so a point like that, right? We call, that is now called a maximum, and a point like this, okay? Obviously the picture is showing that it hits a low, right, and not anywhere lower than that on this graph right here. So on throughout the entire graph, there's nowhere that's hitting as low as this point right here. That's why it's called a minimum, and up here it's a maximum. Okay, and so in that way we now have a definition. Okay. And so you have seen in the picture earlier, there's a peaks and there's a low right there. And so relating that to our understanding back at the days that we're studying in calculus 1 right there, then those peaks and those bottoms, the first thing we call them, those are the local maximum and the local minimum. Okay, so now let's have a precise definition of what a local maximum and what a local minimum is. Okay, so now this is our definition. So a function f of xy has a local maximum at a given point a comma b if the function value at anywhere else, or if the function value is less than or equal to f at a comma b. Okay, for all x and y's inside some disk center at a comma b. So that is the definition of a local maximum. So meaning, now if we're looking at the graph right here, okay, a local maximum means, see, at some point a comma b on the x and y floor, right, this graph hits a peak, and that peak here, at that peak we say it's a maximum, it's a local maximum, meaning at any other x and comma y points the function must reach a value lower or at most equal to that point. And that's what maximum, a local maximum means. And in a disk, meaning, think about if we reach that maximum peak right here at that point a comma b, whatever, right? And eventually we're going to learn that method to precisely find out where that point a comma b is. But now local maximum means it's only true around, for now we only worry about the maximum that's only true locally, meaning for some disk around that, for some region, for some disk around that point like that point where we hit the maximum. Okay, and that's what it is for being a local maximum. And so same way, now when we're looking over to local minimum, a function f of x has a local minimum, right, at a specific point a comma b, right, on the x and y floor if the function value at anywhere else is greater than or equals to the function value at a comma b. Okay, so that precise statement is here for all x comma y inside some disk center at a comma b. So now that we have a precise definition of what it means by being a local maximum and local minimum, we saw on the picture earlier, it happens where the picture was telling the story, and let me try to quickly reconstruct the idea right there. And it's very similar to back in those days that we were studying about single variable calculus. So when it hits to think about a tangent point. So when it hits to a peak high or a peak low right here, the tangent plane will happen to be a flat tangent plane, completely flat, a horizontal tangent plane. So back in the days that we were studying about single variable calculus, then a function reaches, if a function reaches a local maximum or reaches a local minimum, then it has to happen at what we so-called a critical point. And a critical point as a definition is a point where we have horizontal tangent line, or slope zero tangent line. And so we take that idea, that imagination, and we bring that into the case of a function of two variables. And so now here, think about either whether we're at a maximum or a local minimum, local maximum, local minimum. If we place a tangent plane there, the tangent plane would need to be horizontal, a flat tangent plane. And so, of course, when we already made that transition into tangent plane, we don't measure tangent plane being in terms of how flat it is by using slope anymore. Okay, but just think about the ideas here. The tangent planes to those maximum and minimum values got to be a horizontal tangent plane. Or at some point, or some other point, think about calculus 1. There were also occasions where our graph has a sharp corner. So we don't necessarily have a tangent line here. Okay, we have an undefined derivative, but in the end, it's still a point being highest locally. Okay, because we didn't look through the entire graph at all. So locally speaking, this point right here is highest compared to other points, in some interval around it. Okay, and so a point like that is also called a critical point. So back in our days studying about calculus 1, about single variable calculus, then a critical point is not only defined as points where we reach horizontal tangent line, but it's also the point where we have sort of like the non-differentiable points like that. Okay? Those points where we have sharp corner or tangent, the slope of tangent line is undefined, the derivative is undefined, and all that. Okay, and so similarly, there are cases here where your peak becomes very tippy peak right there. Okay, right, very tippy peak. Okay, where we don't necessarily have we can't draw a tangent plane right there. But those peaks right there, think about, there are cases where there are times where those are also considered as the critical points as well. Okay, but then for simplicity, we won't go into that far thinking in terms of those peak points where we fail having tangent line. Okay, so I could have used that term. These are the situations where we fail even having tangent planes here. We fail having tangent planes, but those are still considered as the critical values. But now, for simplicity, we only focus on those cases where the function is differentiable, the function has tangent planes, okay, and being horizontal tangent plane, okay. And so now, in that way, allow me to swing over to the computer. And now we have what's so-called the definition of a critical point. So, as a definition, any point A, comma B in the domain F, in the domain of the function f of x, comma y is called a critical point. So that's the definition of a critical point right now. It's a critical point if the partial derivative of the function in respect to x, the partial derivative f sub x at the point a comma b equals 0, or it's a point where the partial derivative in respect to x does not exist. So that is just like the day that, or I was indicating the tippy point and the tippy point earlier right there. The sharp point, right? That's where the partial derivative in respect to x does not exist. And further, the partial derivative in respect to y must also equal 0, or the partial derivative in respect to y at that point does not exist. Okay, so as long as, so a point is called a partial derivative if both of these are satisfied. Okay, both of these partial derivative of f of x, of f of x, f of y are all equal 0, right? Or some of these does not exist. One of these does not exist. Okay. So that's now how we define what the critical point is. And so now in that way, now we come to an important theorem here. And this theorem allows us, brings us an actual method, a precise method to find a maximum, local maximum, or local minimum. So the theorem says if f of x has a local minimum or a local maximum at a given point, then that point a comma b is a critical point. So it's a guarantee that is a critical point of f of x comma y. So back in what I was saying, so now if we can find, the maximum or the minimum values, the local maximum and the local minimum value of this function is guaranteed by the theorem to happen only at the critical points. Only at the critical points. So that means on the picture here, whichever the point a comma b that gives this tippy point right here, that gives this high mountain, I shouldn't say tippy, this high mountain, or whichever point on the x and y floor that gives this low point right here, being the valley, right? Those are the critical values. Those are guaranteed by the theorem to be the critical values. And so the theorem now states that the theorem, after what's stated in the theorem, it gives us a method, a solid method. Now, hey, in order to find where the minimum and the maximum happens, in order to find where the minimum and the maximum happens, and now I'm talking about the local minimum and the local maximum, we just need to find the critical points of the function right here. Okay, so just like back in the days that we were studying about single variable calculus, before we find the local maximum and local minimum, we got to find the critical values, the critical points. Okay, and so now just like that, we must find the critical points of this function before we can find the maximum and the minimum value right there, because the critical points are where the function reaches local maximum or where the function reaches local minimum. Okay, and so in that way, again, one more time looking back at the definition right here. So as I said earlier, we are taking out for simplicity the case where f partial derivative of f of x of f of x comma y in respect to x does not exist, and the partial derivative in respect to y does not exist. We're taking out these two cases. We're ignoring these two cases right here throughout our lesson. And so now critical points in our lesson here means those points where simultaneously partial derivative of the function in respect to x and partial derivative of the function in respect to y equals 0 at that point a comma b. And so now in that way, allow me to bring in the first example right here. So now I'm going to call that example 1. And in this video lessons, each example is labeled with a number so that I can easily reference back, because all of these problems that I designed in this lessons are really connected in a chain, a problem right here. So now we're starting out with a function f of x comma y equals 8x minus 8y over 8x squared plus 8y squared plus 1. I'm about now to write down the example number 1 right there. So for example number 1, we need to find, okay, let's find all critical points. Okay, so find all critical points of the given function f of x comma y. We need to find all critical points of the function f of x comma y. And so I should have done this before I wrote down example 1, but now this function here before we get started, this function here can be simplified down to, now it's not really a common factor, but I see the factor 8 being present in a lot of terms throughout the numerator and throughout the denominator. And so we can cancel out that common factor 8 right here, making it x minus y over x squared plus y squared, but plus 1/8. And so now for anyone studying with me in this video lesson, you are at a multivariable calculus level, so allow me to assume that your algebra is fluent enough that you can see how I got from algebraically from this. And after reducing the factor 8 away, I reduce it down to this with a little factor 1/8 in the denominator. Okay, but now doing this is going to make the later work a lot easier. Okay, and it's exactly the same function. It's just a matter of canceling that common factor 8 away. Okay, so now I rewrote that function into this form right here. So for our function now, to find all critical points of this function, right? That's the goal of this example 1 right here. We need f sub x and we need f sub y. All right, and so now at this point, needless to say, I could have also mentioned this before we began right here, but you are required to know how to find partial derivative of a multivariable function prior to this lesson right here. So at this point, if you're feeling unsure about how to find these, or you have completely no clue, I recommend to view other video lessons of how we find partial derivatives, or to find learning resources elsewhere before you can proceed with this video lesson. Okay, but now assuming that you already understand or you already learned how to find partial derivative of the function in respect to x, partial derivative of the function in respect to y. Now I'm skipping the steps here because the steps are, again, I'm assuming viewers are fluent with that, so I'm just getting straight into writing down what the two partial derivatives are. So f sub x in my case here, okay, partial derivative along x is found to be minus x squared plus y squared plus 2xy plus 1/8 over x squared plus y squared plus 1/8 all squared. So that's my partial derivative in respect to x along the x-axis. And then I also have found, or in another way of saying, the partial derivative for the function in respect to y, okay, was found before I made this video lesson. Minus x squared plus y squared minus 2xy minus 1/8. Okay, x squared plus y squared plus 1/8 all squared in the denominator. And so for anyone viewing this lesson, I highly recommend that you quickly pause the video, okay, and double check your work with that to make sure it agrees with me. Okay, and so now assuming that you have already paused a little bit and checked the two partial derivatives here, back to the definitions. Being a critical point, we need both. A critical point is a point a comma b where the partial derivative in respect to x at that point a comma b and the partial derivative in respect to y at the point a comma b both equal 0. Both equal 0. And so in that way, now we are going to purposely set, because we need to find where those points are, making the partial derivative in respect to x and the partial derivative in respect to y equal 0. So in that way, we are setting, okay, we are setting the partial derivative in respect to x to equal 0, and at the same time, we want the partial derivative in respect to y equal 0. So this is what we purposely set. We set for, hey, finding the x comma y points, all of those x comma y points, satisfying partial derivative in respect to x equals 0, and simultaneously f sub y of x comma y equals 0. So that means we produce, so provided the two partial derivatives already found, we produce for ourselves right from this logic right here, right from this fundamental, we are leading to a system of equations. So it's just my style that I write a system of equations that with two equations, right? And I use a curly braces right here to sort of tie them together. So we need to find simultaneously all those pairs x and y satisfying. How about minus, okay, x squared plus y squared plus 2xy plus 1/8, okay, all over x squared plus y squared plus 1/8 all squared equals 0. So we got one equation. And it looks like I'm going to need to extend this even further out. So this is partial derivative in respect to x equals 0. And simultaneously, I need minus x squared plus y squared minus 2xy minus 1/8. All of that over x squared plus y squared plus 1/8 all squared to equal 0. So now I have produced for myself a system of two equations. A system of two equations. All right. And so I do admit that I brought in a function that at about a mid-level between the easy and difficult. So this function that I brought in is about a mid-level. So when it comes to solving a system like this, okay, you can use the algebra to solve it, or you can use some advanced mathematical software to solve a system like this to come out with whichever points x comma y satisfying both equations right here. And I can tell you the reason I set the function I brought in being a mid-level in terms of difficulty and easiness, and because you can still for an equation like this, you can still solve algebraically, or you can solve using the computer. Okay, and so I'm leaving the steps to solve the steps to solve algebraically out, and I can at the end of the video will give that optional section, that optional length on the video at the end to show you the steps how I get the answers here. But if you don't like the steps using the algebra, you can also use a computer machine, a computer software to solve the system here. But now solving this system simultaneously, I find two pairs of value. So it leads to one pair, 1/4, comma, negative 1/4. That's one critical point I found. X comma y, okay, that's one of them. And I found another one being minus 1/4, comma, positive 1/4. So actually, my work that I went through came out with two critical points. And I call these, once again, ladies and gentlemen, these are the critical points, because solving this system of equation, so these are the 2 points, x comma y, that simultaneously satisfy both equations here equals 0. Both expressions here, both partial derivatives equal 0 at these two given points, x comma y, x comma y. All right, so we found two critical values. So that is how we found the critical values. Very similar to the days that we are doing calculus 1, single variable calculus. We got to set the derivative equal to 0 because we want to find out at which x value is giving us horizontal tangent line. So here, these are the places, these are the points on the x and y floor giving us horizontal tangent planes. Okay, horizontal tangent planes. But now, before I proceed, think about it. These are just critical points. They give horizontal tangent planes. So that means we will reach two horizontal tangent planes at these 2 points right here. Which one of these, okay, before we substituting these into the function, which one of these will give us the maximum? And which one of these will give us the local minimum? That's the question for the next step like that. Okay. And so now on my computer screen right here, I have a theorem. And this theorem is commonly known among the mathematical professionals out here. That they call that the second derivative test. Or for any students, we introduce this theorem commonly as the second derivative test. So this theorem is stating that let a comma b be a critical point of some function f of x comma y, and assume that f sub xx, second derivative, second partial derivative, okay, f sub xx, f sub y, and f sub xy. So these are the important ones. And these are all the second derivatives, second level partial derivatives. F sub xx, f sub y, and f sub xy. And so, before I proceed further into this lesson, again, anyone who is not familiar with f sub xx is, or f sub y is, or f sub xy is, make sure you've learned what those are before you can proceed. Those basically means the second derivatives, but second partial derivatives, okay? But allow me not to go too far back into those basics like that. So make sure you understand what those f sub xx, f sub y, and f sub xy are before we can proceed, okay? But so now, assuming that you already know what these are, right? And so assume that those second partial derivatives are continuous around that point or near that point a comma b. Then now we're setting up the following quantity d right here. So now, in order to proceed on to understand that theorem, I must swing over to the board here and explain what that d being introduced in the theorem right there. So, without having so much space on the computer, I gotta write the d here, but d is a quantity defined by the following. So at least you know that the theorem here requires your partial derivative fxx and your second partial derivative xyy and your partial derivative fxy. So d here is defined as following. Fxx times fyy minus fxy all square. So this is the definition of what that d expression is. So think about the second partial derivative fxx and second partial derivative at fyy. You can evaluate these at the specific point a comma b, and then you can also evaluate f sub xy right here at a comma b, and then do the square. This expression right here is called that d expression. Okay. Now, if anyone finds this expression hard to remember, there's an easier way to remember. Think about a determinant as following. We go first row in the determinant, it's f sub x, and switch over to f sub xy. So all of the first derivative, f sub x are here, but then second derivative in terms of x and y. Okay? And then we have the next row, f sub yx, and then f sub yy right here. So think about the orders like this. Again, I mentioned that earlier, and I hope viewers are understanding, but think about as far as the level, the first row is for all the first partial derivative being in terms of x. And then we take in turns the second partial derivative in terms of x and y. And then for the second row of our determinants, we're taking the first partial derivatives are all in respect to y. And then in turn, we're taking the second partial derivatives in respect to x and y. So columns here are for the order of this second derivative in terms of x, in terms of y in the column. And then the rows here is indicating the first derivative for x and for y. Okay? So that's how we calculate the d. And we have learned previously that, see, writing down a determinant, that means we multiply these two diagonal entries right here. That's why we have that. And then it's going to be minus. And it's going to be minus f of xy times f of yx. But wait a minute. We have learned earlier that f sub xy and f sub yx will always equal. That's why it ends up with this. Okay? And so now I can take this away. And the way to arrive there, I found in my years of teaching, students remember better with this, thinking of the d expression as this determinant right there. Okay, but either way you want to take it, right? Either you go with that direct formula or think of that as this determinant. So that's what the d in the theorem I put on the computer screen earlier is talking about. And so now we are ready to get back to the computer screen and advance on to read into that theorem. All right, so now if d is positive and f(x(x) at a comma b is also positive, so that means we have to substitute this point a comma b, as, assuming it's a critical point. I mean, provided it's a critical point. We gotta substitute that critical point into the d expression and into the f(x(x) of our function. If both of these are positive, then the function will have a local minimum at this point a comma b, or the function f has a local minimum at that point a comma b. And then similarly, now again, when you're substituting that a comma b point into the d expression and getting a positive d, but then your f sub xx at that point is negative, this is the switch right here, then the function f has a local maximum here at that point. And then there's a case, there could be time where the d expression falls negative. This is where the function has a saddle point, and I will get back and explain what that is here. Okay? And then of course there are also cases where d equals 0, where the test fails. I will spare some time at the end of the video lecture to discuss a little more about what situations are making the d equals 0 over here. But usually we don't have to get into that far extent right here. Okay, but I will definitely spend some time explaining what a saddle point is. Okay, and so now in that way, the theorem is making it clear. That's the way, that's the method to determine whether the critical points we have found, or any one of the critical points we have found, will be classified. Right? Will be classified as either a local maximum or a local minimum. Okay, and so now in that way, I'm going to head over to the other board. All right, so now that we have found, think about one function we have done in a sort of like a step one through our example one. We have found the two critical values, right? From example one, we found two critical points actually from this function. So now I'm going to bring in example two. So example two here, many textbooks label the problem as following: classify the critical points. Classify the critical points. Okay, but classifying the critical points really means, as far as a verbal explanation or another way of describing the situation, we just want to determine, right? Determine whether each critical point is a local maximum or local minimum. That's what it is. That's what classify the critical points means, and we find this standard way of wording it throughout many textbooks, but I just want to give a further clarification. That classifying the critical points means we try to find out on each. So if we found two critical points, we gotta determine which ones among there is a maximum and which one there is a minimum. So if we have to go through each point and decide, is it a maximum or is it a minimum? Okay, and at one critical point, at each critical point, only one of the two cases happen. Either it's a local maximum or a local minimum. It cannot be both. Okay, but that's what it is. Classifying the critical points means we determining whether each critical point, right, is a local max or a local minimum. So now, once we have a nice, thorough understanding, I'm going to quickly erase this. Let's find it. So, according to the theorem that people most of the time refer to as the second derivative test, right? And that is the second derivative test. Then we need f(x(x), f(y(y), and f(x(y). Okay? And so, assuming that viewers who've learned along with this lesson here already know what f(x(x), f(x(y), and f(y(y) is, just knowing what that is, then I am going to just skip the steps, but just write it down to what those f(x(x), f(y(y), and f(x(y) are. Okay. So now for my function, for our function here, we already found fx, fy, And so f sub x, f sub y we found earlier. So now fxx, this is what I found right here. We have 2x cubed plus 2y cubed minus 6x squared y minus 6xy squared minus 3/4 x plus 1/4 y all over x squared plus y squared plus 1/8 cubed. I highly recommend that you pause the video, do your own work to make sure you agree with my fxx here. All right, and now assuming that you have checked, right, and convinced yourself that this is the fxx, assuming that you are able to carry out the steps on your own. Now I'm going to write down fxy. Fxy for our function, this function, is going to be 2x cubed minus 2y cubed plus 6x squared y minus 6xy squared plus 1/4 x minus 1/4 y, and over x squared plus y squared plus 1/8 cubed. All right, and I had to also spend a little bit of time quickly glancing through whether I had any typo when I wrote it on the board here. And now for fyy, last one that we need. Minus 2x cubed minus 2y cubed plus 6x squared y plus 6xy squared minus 1/4 y, x plus 3/4 y. And divide all that here by x squared plus y squared plus 1/8 all cubed. So now we have found fxx, fxy, and fyy. fxx, fxy, and fyy that we found. So now in that way, at this point right here, we have everything ready. So what we need is to throw all of these into our settings right here. See what we need: fxx, fxy, fyy, yx, and fyy. We need to throw all of these in here to do that determinant thing, to get fxx times fyy minus fxy all squared. But so that's why I said earlier at some earlier point right here, but I chose the function for this lesson to be a function where about at the mid-level between the being easy and being difficult. So it's about a mid-level, and so consequently it brought us into these complicated looking fxx, fyy, and fxy. So in that way, if you are patient enough, you can directly substitute these general expressions in there and do your math. I'm not saying that we cannot do, but we can do it. We can do things a little more, being a little bit smarter. Okay, we can be a little bit smarter in terms of doing these. So yes, eventually we will get the D right here, but we can always substitute the critical values. We found the critical points. So I remind anyone watching the lesson here, one critical point we found is at 1/4, comma negative 1/4. And then another one we found is at negative 1/4, comma 1/4. We can substitute these points in turn into the three second partial derivatives here, and then evaluate the D expression here after we successfully substitute it. All right, and so in that way, I'm short of space, so allow me to clear out my board right here. All right, so I used a calculator aside from what's on the board here, but f(x(x) at the critical value 1/4, comma negative 1/4. So this is the first point that we consider. So let's look at that first point, 1/4, comma negative 1/4. Okay, so let's focus to that point first. So I substitute that critical point into my f(x(x). Okay, my computer calculator came out with the following value: negative 16. My computer calculator also gave me f sub xy at this value, at this point, 1/4, comma negative 1/4, coming out to be 0. And f sub yy at this same point came out according to my calculation, negative 60 as well. So we got all the values. So now we are ready for calculating the d expression right here, the determinant, that determinant expression right here. So in this case right here, our d is calculated as, see, f sub xx negative 60, f sub xy at that point 0, f sub yy at that point, f sub yx, which is the same as f sub xy at that point 0. F sub yy is placed here, negative 16. So now, working through the determinant, we are looking at minus 16 times minus 16 is minus all 0, so it's positive 256. Positive 256. So now we know that at this point, 1 comma negative 1, 1/4 comma negative 1/4 here, the determinant is positive. The determinant is positive. Okay? And now further, the f sub xx at this point, 1/4 comma negative 1/4 is found previously here. Is a value negative. It's a negative value. All right, so now, one more time, let's look at the statements in our second derivative test theorem here. Okay, so when the d is positive and f(x(x) at a comma b is negative, then the function has to reach a local maximum. Okay, a local maximum at that point a comma b. So now a comma b in our problem here is specifically 1/4 comma negative 1/4. So now we have a conclusion. That means this function right here, now we found as a final conclusion, this point 1/4 comma negative 1/4 is a local maximum value. Okay, local maximum value. So we have classified that. This is how we classified it. So this point here is classified as a local maximum. It was a critical point before we did the second derivative test. And now after working through the second derivative test, we classify this point as a local maximum. We have one more point to go. And so the other point we have here is that point at negative 1/4 comma positive 1/4. All right. And so for this one right here, in order to test that, right, and classify it, okay, I'm going to put that in f sub xx. Okay, I'm going to substitute that into f sub xx. So I'm going to use my calculator on the computer here to calculate this. And then I will also need to calculate f sub xy at this point, negative 1/4 comma 1/4, to come out with some value. I am also going to calculate f sub yy, right, at negative 1/4 comma 1/4. So let's look at the result here after I come back from the calculator on the computer. All right, so my calculations on the computer show that at this point, negative 1/4, comma 1/4, I have f sub xx equals positive 16. At this point, negative 1/4, comma 1/4, I have f sub xy equals 0. And this last one here also equals positive 16. And so now, again, we are ready for setting up. And you can see before we setting up the d right here, f sub xx at that point is positive. And now I'm calculating that d setup right there. Okay, so now it's f sub xx being 16, f sub xy being 0, f sub yx, which is the same as f sub xy, 0 here. So think of that as f sub yx. And now here is a f sub yy, it's positive 16. The calculation will come out after this determinant, 256 again. Okay, so here we're looking at, at this point, this determinant turns out positive, this d expression. And further, this partial derivative fxx at the point negative 1/4, comma 1/4 is also positive. That leads us to a conclusion that, hey, this point negative 1/4, comma 1/4 is now a local minimum. All right. This is now a local minimum. That's how we're working with that. And so now let me put the graph back so that you can convince yourself right here. So we found two critical values, two critical points right here. All right, so here's the graph once again. Now, as far as the picture, it tells that we have a local maximum right here. So now I turn the view of the graph. So positive x-axis is here, positive y-axis is along this way right here. So this point obviously seems to be right at, apparently seems to be right at positive 1/4, but negative, positive 1/4, comma negative 1/4. It gives us a positive, it gave us a local maximum. And right here, see, we had a local minimum right there, right? And so now as we turn the view right there, positive x-axis going this, positive y-axis going this way, negative x-axis going that way, so the point is about right there. So negative 1/4, comma positive 1/4. That point was classified mathematically on the board earlier as giving them local minimum. So that's how it was done. That's how it was done. We found, so example 1, just like the standard, think about those days that we were doing the finding maximum and minimum value problems in single variable calculus. And we got to first find the critical values. So now example 1 was intended to be those equivalent kind of problem that we find the critical points. And then after you found the critical points, we got to classify the critical points. Among them, who's the maximum? Among them, who's the minimum? Okay, so on each one of them, is it a maximum or minimum? On the next one, is it a maximum or minimum? So that's why this is the intention of example 2. All right, so now we have successfully classified, and we have found only 2 critical points ever throughout the entire domain of this function. And so now, and we found only 2 critical points, right, giving flat horizontal tangent points. And so now, the next problem I want to bring in as example 3. Because after example 2, think about it, we only found where we only found where the graph reaches the maximum and where the graph reaches the minimum. But we want to find out how high does it reach and how low does it reach. And so the final problem is here. Let's say find our local maximum. and local minimum values. So now we're talking about the actual values. How high does it reach graphically or on the graph, and how low does it reach on the graph surface right there. So now it's just now a matter of the function at maximum value. That's just my style of writing it. The maximum function, the maximum value of the function locally equals to the function value at, so the critical points that we have decided earlier being the 1/4 comma negative 1/4 is the one to reach the maximum. So we substitute that into the function, into the beginning function. So 1/4 comma negative 1/4. We saw that on the picture. So now we're gonna go ahead and substitute this into the function, and we will have whichever value that will come out. It will be the local maximum value. Okay, so my calculation came out being positive 2, and you can do the same on your own independently by substituting this pair of values into our initial function, into our beginning function right here, and you should come out with positive 2. On another hand, so now minimum value for our function. It's just my style, maybe similar with many other professors out there, but f minimum, the local minimum for our function, is the function evaluated at that critical point where we call that reaches the local minimum here. So negative 1/4 comma 1/4. We substitute this pair of values into our beginning function. My calculation came out negative 2. So the function hits as low as -2. That's the lowest right there, at least in the area that we can see on the graph. At this point, negative 1/4 comma 1/4. So we found all of the local maximum and minimum values. All right, so now back on this theorem, which we popularly regard as the second derivative test. So these two statements right here, let me give some graphical insight, and then we won't have to, for the lesson here, we won't have to even get into any of these complicated situations right here. But so if the D expression, right? So in our examples we've done earlier, the D expressions were all evaluated to be positive. And what matters to give local minimum or local maximum relies on the partial derivative fxx right here, whether being positive or being negative. But now what happened if the D expression evaluated and come out being negative? The theorem here stated that the function f of x has a saddle point. So what is a saddle point? So now let me swing over to a graphing space right here and allow me to use a couple pictures right here to describe what a saddle point is. So now I'm going to bring up the graph of some other functions aside from the one that we were working through our examples right here. But let's look at this one right here. So there's some function giving us this surface. Okay, and so in a way how we've learned, then clearly these 2 points right here are the valleys, right? And these are the local minimum. So needless to argue about that. But what's the saddle point? If you're looking right here at that point, so it looks to me through my eyes right here, right at that point about 0, 0 on the x-axis, on the x and y floor right here. You see on one way at that point it's going maximum, but then if we're looking at another view right here, it goes minimum. So that's what saddle point means. Okay, sort of like a saddle, like a saddle that you're putting on a horse. So it has this picture right here. It has this picture. Okay, it's going minimum in one way, but then it's going maximum in another way. So that's kind of like that. Okay. All right, so I'm trying to make my best of drawing the picture right there. Okay, so it's a point like that. It's called a saddle point. All right, so that is when the D here, that is when the D, so a point like that, and there could be time it comes like that, but a point like that is neither a maximum or neither a local maximum or nor a local minimum. So that's where D is negative. Okay, and so let me swing back to the graph one more time. And there are other, let me bring in another graph that looks more trivial with the saddle point right here. So let's look at something like this. Okay, we have a local maximum here, but this point right there, about these right here, they are saddle points. All right, see, they are maximum in one way. See, if I turn it this way right here, see, they are maximum in one way, but then they are also minimum in another way. That's why these points right here, they are the saddle points. Okay, and so at those points right there, we know that we're gonna have negative D expression right there, that D expression being negative. And now for something like this. All right, we have a minimum. Seems like we have a low values, right? But it's like the whole, it's not only at one single point, it's like for a whole line of values right there. On the x and y floor, like a whole trace, a whole path where we reach the low values right there. So this is a case where it describes that we having the D expression equals 0. So something like this is equivalent to the D expression equals 0, or in other words, if we use a second derivative test right here, we fail. It's not telling us. So, well, for beginning multivariable calculus, we almost never have to face with a problem like this, okay, where the second derivative test fails here. That we'll wait for a more advanced course so that we can learn to handle. Okay, but that's just right now I'm using the graph here to describe that there are cases where the D equals 0, which the second derivative test fails again. Okay, that means we have to find other way to argue that we do reach minimum or we do reach maximum, but it's not working out together with or it's not consistent with the second derivative test. All right, so the three examples we've gone through brought in for us a certain guidelines. Thankfully that this guideline right here is quite constant, is quite permanent. Okay, throughout a lot of our finding maximum and minimum values problems right here. But so what is that guideline? Example 1 brought out that, think about sort of like the first step in any time you're finding a local maximum or local minimum value problem right here. Then generally speaking, right? Finding local maximum or local minimum value. Example 1 brought in for you that first step here is we have to find all critical points. And so the method is done throughout, it's carried out just like how we did example 1. And example 1 really brought in the first step in the method of how we find local maximum and minimum right there. After we put all three examples together. And then step 2 right here, think about example 2 that we did. After we found all critical points, we got to classify all of the critical points. So classify all critical points. And this is where we use the second derivative test. Right, and this part right here may be it could be the most time consuming one due to the fact that we got to find the second derivative, three partial second derivatives, right, and then evaluate them and then put them in the determinants, right. So the essential part right here to remember is that determinants f of the xx, right, f sub the xy, f sub yx, and f sub yy right here. Think of that determinant right there. So we got a lot of work in this step 2 right here. All right, and then step 3 is to substitute your critical points that you have already classified, substitute them all into your function. And so we find the local maximum or minimum values, right, by substituting it substituting the critical points into the function. Right, so that introduces for us the steps right here. After the 3 examples being put together, that introduces for us the steps of how we can, on standard, find the local maximum and the local minimum values of a given function.